Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
That's so cute. I want to be the universe's friend, and I am.
And you are.
I am Dr. Moiya McTier. I'm an astrophysicist. That's where I got the degree in being a friend to the universe, and a folklorist, and I'm so happy to be here.
And I'm Corinne Caputo, a writer and comedian, and I was like, there's a third thing I am. Well, I have been rug tufting a lot this weekend, so... That's the third thing I am this week. If you hear me coughing throughout this episode, it's because I need a high-quality mask. And I just, breathed in all these, fibers and immediately Googled it. Tons of textile workers have died from this. And I'm like, okay.
Corinne, please don't fall prey to a death from, the 1800s industrial revolution. Don't do that.
So, I do love vintage stuff, so let me back.
We would like to keep Corinne Caputo, writer, comedian, and rug tufter around.
I just gotta start tufting outside is the answer.
Corinne, we live in a time of masks. I
know. I put on my best. The one that I have is the best, but it still got in. But I love where we are right now.
Yes. Oh, okay. So, like we said last week, it was my birthday. And so for my birthday trip, after I got my birthday hairdo, I wanted to visit some giant, loud animals in a warm place. So today, we are recording at an elephant sanctuary in Hohenwald, Tennessee. I have never ridden an elephant before, but we have appointments to do that right after this recording. And they're just so cute with their big trunks and their floppy ears. And they're loud, but good for them. They should be taking up space, both physically and orally.
I encourage that. Yeah, we should be yelling whenever we want to. I love it. Elephants are one of the cutest cartoons you could see.
Oh, that's true. There are a lot of cute cartoon elephants. But the Hanna-Barbera cartoons, they were...
Oh, yeah. I'm like, is Dumbo the only famous elephant cartoon? It's not. That can't be true.
He's definitely not. But even if he were, he's cute enough to make this claim still make sense.
With the big ears. I have never ridden an elephant either. I have ridden a horse. That was scary for me. I'm not a horse girl.
I imagine this is just going to be more extreme in all ways. You'll be higher up. You'll have a wider... seat. So maybe while we're recording this episode, we can do some groin stretches.
That is what I'm going to need.
Yeah, okay. So please excuse us if we make any winces or sounds of pain while we're recording this episode, because not only are we surrounded by elephants, but we're also doing just some quick stretches and calisthenics here, apparently.
Yeah, a good old-fashioned warm-up.
Okay, but while we are surrounded by all of these gorgeous space-taking elephants, we're going to be discussing an interesting topic in astronomy, and that is, how fast are we moving through space?
I am so excited for this. I know it's fast. I have no idea how fast.
Right. Well, when do you think you realized we were moving, Corinne? Because it's not an obvious thing.
Yeah. I think that it was, I have this memory of elementary school life where you're I don't know, I feel like so much of childhood is kind of getting these nuggets of knowledge and not rubbing it in other kids' faces, but using it all the time. So it's you think that's fast? Well, we're on a roller coaster right now. We're just saying little things. Maybe I was just a horrible child. This is what I did, but
you're just a smart ass, which is great.
I just have memories of learning that and holding so tightly to the fact that we are moving and I am moving.
Good. So it's less of you remembering a time when you realized this and more that you have difficulty remembering a time before you knew that we were moving.
Yeah, exactly.
Love that. The human species cannot say the same. For so much of humanity's history, we believe that we were the center of everything. And only in the last 400 years or so did the public en masse start to believe that we're moving around other stuff. So now that we know we're not the center of the universe, we have to answer this annoying question of, okay, well, if we're not standing still, how fast are we moving and in what direction and why?
Yes.
So there are a lot of ways we can answer this question. We're gonna have to dig into some layers, but I'm ready.
I'm ready. I am ready.
Okay.
My elephant ears are open.
Oh, good. So first of all, we need to establish that speed is relative. Anytime someone gives you a speed like 65 miles an hour or 125 kilometers per second or whatever it happens to be, that speed is relative to some stationary object. So like Corinne, if I were to throw a ball 20 miles an hour at your torso, that is with respect to your torso, right? Like your torso is the reference frame. That's what's standing still. If you were running though, like if you were running towards me, and I threw that ball at you, from my perspective at 20 miles per hour, it wouldn't hit you at 20 miles per hour because you're running towards it. You're not stationary. You've added your own speed to the equation. So they get added together, actually. Like if you were running at 5 miles an hour, the ball then hits you at 25 miles an hour.
Whoa.
But if you were moving like the other way, then it's subtractive and the ball hits you at 15 miles per hour. So everyone remember that speed is relative to some point of reference. And that gets weird when we're talking about space because what should the point of reference be in space? This gets into very confusing stuff about coordinate systems and reference frames. Some of the banes of my existence when I was doing astronomical research were the fact that people did not clearly say what reference frame and coordinate system they were using often enough. Like I did this one project where I was trying to figure out how fast stars were moving in our solar neighborhood, like in our little part of the galaxy, and how that affected their ability to hold on to exoplanets. And I had to establish a coordinate system, and I was taking in data from the Gaia spacecraft, which tells us how fast stars are moving around the galaxy. But they were using different coordinate systems. Like one of them was using the position of the sun as the reference point for the coordinate system, and others were using the center of the galaxy. And they didn't say.
Oh no!
And it was very confusing. This is just like an endless rant that I can always go on. But remember, speed is relative. It's always important to define what your reference system is.
Yeah. So much of my experience with speed is I was briefly on the track team in high school, and I never knew like what was a good race or not. I mean, it's also track is so personal. Like what can my body physically do? But even now, if my husband or someone is like, whoa, someone just did like a marathon, like at this speed. And I'm kind of like, you got to tell me what a normal person would do it at before I understand. It's like the Olympics where I'm like, I actually need a regular person to be trying this just off screen so that I can like cut back and forth and see and prove this is an amazing feat.
Oh, I agree 100% with you. There should be normies.
Yes.
In the Olympics, just to show, because it doesn't look impressive when everyone is so good at it.
And
but
they
I know
deserve to be impressive. Like they deserve to make me think they are impressive. But my stupid little brain is like, I need to compare this to something else. So it's all relative.
It is all relative. But that actually brings up an important but subtle, I think, distinction here. So relative. Even the definition of relative is relative. So you're talking about relative speeds in terms of how the speeds compare to each other. But when I say speed is relative and we need a reference frame, it's not a reference so that you know how much faster or slower something is than something else. Although I guess it is. It's reference frame and that like you need to know where you are standing as you're watching this thing move around.
That makes sense.
So with that caveat that speed is relative, we can try and find like the total velocity of us on Earth through space. And that total velocity will be the sum of the Earth's rotation speed about its axis, the Earth's orbital speed around the sun, the sun's orbital speed around the galaxy, plus the galaxy's motion towards something that we'll talk about later, plus our entire galaxy cluster's motion towards something even bigger than that.
Oh my
It's
gosh.
a lot of motion.
That's a lot.
It's a lot.
A lot of movement. My Dramamine is coming out.
Yeah. So we'll go through each of these factors in the equation and explain what each of these speeds are and whether or not it has any fun consequences, starting with how fast is the Earth rotating on its axis.
Ooh.
Do you know how fast?
Well, it rotates on its axis every day.
Every day.
Yeah, so 24 hours.
Yeah, so this is an equation that you can do. In general, you can do most of these with equations. And the equation is how far are you traveling and how long does it take you to travel that distance? And if you divide the distance over the time, that gives you the velocity. Here, when we're talking about the Earth rotating about its axis, we have to know where on the Earth we are. So just a little bit of context. When I say Earth's axis, that is the line that runs from the geographic North Pole. Remember our episode on
Not
Aurora?
where Santa is.
Well, no, that is where Santa is. Yes.
Geographic is where Santa is.
Yes, the geographic North Pole where Santa is. So the line runs from there to the geographic South Pole. And that axis is tilted towards the sun with like a 23-degree angle, and we can talk about that in a future episode. But that is what the Earth's axis is. And that line is the line around which the Earth spins to get our day-night cycle. So at the equator, you're standing at the widest part of the Earth. So the circumference at the equator is about 24,000 miles. That's like if you take a measuring tape and you put it around the Earth at the equator, it would be 24,000 miles. If you're staying at the equator, you travel 24,000 miles in 24 hours. So your speed is about 1,000 miles an hour. But when you're standing at a different latitude, if you go any north or south, you actually travel less distance in the same amount of time.
Okay.
So let's say you're moving towards the South Pole and you're at a latitude of like 50 degrees south or whatever. You are now at a point of the Earth where the circumference is much smaller. You can do trigonometry to figure out what the circumference of the Earth would be at a certain latitude, but instead of 24,000 miles, let's say that it's like 17,000 miles in circumference. And you travel 17,000 miles in 24 hours. So your speed is technically slower as you move away from the equator.
Whoa.
Yeah. So that's the rotation of the Earth. This does have some interesting consequences to our weather and our climate. If the Earth didn't spin at all, warm air would be able to go from the equator. It would rise up and travel to the poles, to the North and South poles, in straight lines. It would just go back and forth between the equator and the poles. But the Earth does rotate. So you get this complicated twisting of the air in the atmosphere over the surface of the Earth. It gets twisted to the side because it's like trying to catch up with the rotation of the Earth. And that gives you something called the Coriolis effect, which is responsible for a lot of energy and heat transfer and weather patterns in our atmosphere. It's named the Coriolis effect because of the French scientist who discovered it. So that's Gaspard Gustave de Coriolis. It's the best I'm going to say that. And this twist or bend in the path of air due to the Coriolis effect can create weather like cyclones and hurricanes, and gives you like Gulf streams and everything. So a lot of our weather comes from the fact that the Earth does indeed rotate. And if it rotated at a different speed, these weather patterns would be more or less extreme. I did this thought experiment in my other podcast, Exolore, where I imagined a planet that rotated much quicker. Instead of 24 hours, it rotated once every 18 hours. And we imagined what like the fun consequences of that would be.
That's really cool. What was one of them?
One of them is that, so it happens here on Earth too, but the effect is smaller. You technically weigh less at the equator because the centripetal force as the Earth is rotating counteracts the effect of gravity just a little bit.
Oh, wow.
So on a planet with a faster rotation speed, that effect is magnified. So you weigh less at the equator. All of the water, or much of the water, rushed to the equator, again, because of the centripetal force. And so what we ended up with was this band around the equator where it's mostly water and a few mountains that peak up. So we imagined like a bird type species inhabiting the planet. And like once a year, the birds who usually live at the poles, they come to the equator and they have a big orgy. And that was...
As I'm sure they would if that were real.
It's surprising how many of my worlds end up with orgies on Exolore.
So funny.
Or maybe it's not surprising. I don't know. But this is not a world-building podcast. All you need to know is that the Earth at the equator spins about 1,000 miles per hour, and if it were faster or slower, we would have different weather.
This does make me think, like, and I've thought this so many times through these episodes, that the circumstances for humans and Earth are so specific and, like, so perfect that led us to this. Like, gosh, how lucky are we that this is not an 18-hour day?
Yes,
and not
exactly. Although, that does bring up an interesting point. And Corinne, there's a little pop quiz here. So, right now, the Earth takes 24 hours about to do one full rotation. Do you think that speed has been constant throughout time? Or are we slowing down, or are we speeding up?
Ooh, I feel like we're speeding up.
Okay, why?
I don't know. I'm imagining like some kind of, like if I spun a dreidel or something, like it slows down and stops. But I don't think that we're going to stop, or at least I hope not. So I'm just praying that if anything, it just picks up pace.
Okay, so when you said you think we're speeding up, what you meant was that you hope.
This is a deep hope.
We're speeding
This
up.
is a deep wish that I'm manifesting by saying it out loud.
All right, well, Corinne, I have bad news for you.
Oh, no.
We are indeed slowing down. If you went back to, like, I don't know, 2 billion years ago, the rotation period of the Earth would have been closer to 18 hours. It was probably about like 20 hours.
Oh, wow.
Several billion years ago. We are losing about 1.8 milliseconds every century. So every century, the Earth day becomes about 1.8 milliseconds longer.
That's fine with me. Like, it turns out this doesn't affect me much because I'm going to die. Because I'm going to stop spinning.
Right. Yeah, it's 1.8 milliseconds per, like, human lifespan. That's totally fine. And listeners, you couldn't see it, but Corinne, I really did see the gears turning in your head to determine whether or not you were okay with this fact.
Yeah, I checked in with all of the parts of me, and we were all like, yeah, it's good to go.
Remember when I told you that the moon is moving away from us by about 1.5 inches
That's
every
what I
year?
was thinking just now.
It is related. It is indeed related. Our Earth spins, and that takes energy. It takes energy to make the Earth rotate. And the moon is slowly stealing away a little bit of our rotational energy every year. So the moon moving away and the Earth slowing down, they are linked.
I'm okay with the moon doing that, too. The moon can take whatever it wants from me.
Okay, cool. Right, because the moon is for the people.
The moon is for the people.
So the people should also be for the moon.
Yes, absolutely. I'm going to think of ways we can support the moon later.
Okay, good. Because now we need to talk about the Earth's orbit, or the Earth's revolution. It is one of my greatest pet peeves as an astrophysicist when people confuse rotation and revolution. Rotation is spinning. It's about an axis. Revolution is orbiting. It is around some central point. So we are revolving around the sun. A revolver, those chambers, they revolve around the central point, right? Yes. So rotation does not equal revolution. Let's all remember that. This can also be done to calculate the revolution speed of the Earth. This can be done with that same equation, taking the distance over the time. So we know that we are about 93 million miles from the sun at any given time. With that number, we can calculate the whole circumference of our orbit. So how far do we travel over the course of a year? I'm not going to ask you to do that math, Corinne. Don't you worry.
I think it's 6,000 minutes. Which is not even a number I just said.
It's not the right number. It's not the right units, but like your heart was in the right place, Corinne. And I would, honestly, when you started saying that, I was a little bit shocked because it is about 500, whatever.
Does it start with a 5? It
does start with a 5.
This is the one thing I know well.
So we travel around the sun about 584 million miles every single year. If you divide that by about 365 days and then do unit conversions to miles per hour, we are traveling around the sun at about 67,000 miles per hour.
Oh my God. That's fast.
Right. So at a time when the speeds just happen to line up so that we are rotating in the same direction that the Earth is going around the sun, and like we always are, our rotation is in the same direction as our revolution, which is really nice. But we would be traveling at like 68,000 miles per hour because we add them up. Just a little bit of information about planets going around the sun and especially Earth's orbit around the sun. It's not a complete and perfect circle. It is what we call an ellipse, or we say that this orbit is eccentric. And the Earth is the third most eccentric planet in our solar system after Venus and Neptune. So Venus has a nearly perfectly circular orbit. Neptune has a slightly less circular orbit, and then Earth is right after that. Other planets in the solar system have even more eccentric orbits, meaning their orbits are even less circular than ours. But that means, because it's not a perfect circle, sometimes we're further away from the sun and sometimes we're closer to it. When we are furthest away from the sun, that's called aphelion. And at that point, we're about 94.5 million miles from the sun. The opposite is the perihelion. That's when we are closest to the sun. And then we're about 91.4 million miles. So it's a difference of like 3.1 million miles, which is big.
Yeah, this is the opposite of like the seasons I would expect. But that's me thinking the U.S. is the center of the world. Like the seasons I experience are...
That is the confusing thing. So a lot of people think that seasons are caused by the Earth moving closer and farther away from the sun. The seasons are actually caused by the tilt of our axis, which is why I briefly mentioned it earlier. But it's counterintuitive if you live in the northern hemisphere, because during the northern winter, slightly just a few weeks after the December solstice, that is when we are closest to the sun. So, take that. Northern hemisphere centrism. You can calculate a planet's speed going around its star if you know that star's mass and how far the planet is from the star. This equation that we use is called Kepler's third law. We should do an episode on Kepler and Newton's laws. That would be fun. I love how I'm just using these episodes as a way to document what episodes we want to do in the future.
Yeah. I'm like, I should jot this down.
But Kepler's third law relates the period of a planet as it orbits to the distance that it orbits, or in astronomy terms, we call that the semi-major axis of the planet. And it goes that the period squared is proportional to the distance cubed. So if you know how much a star weighs and you know how far a planet is from it, you can figure out how long it takes that planet to go around the star. But planets can move in a solar system. They can migrate in and out. Like they can move closer to the star, they can move further away from it. And we are pretty sure that this has happened in our solar system. People have done simulations of the early solar system, and they think that especially the gas planets have moved around a lot. I saw this one simulation, and it will be included in the research notes for this episode, from a paper from a research project saying that Uranus and Neptune were much closer to Saturn at one point, and that Neptune was further in, so it went Neptune then Uranus. But then they migrated and they swapped places.
Wow.
And so this happens often. For a long time after we started discovering exoplanets, one of the most common types of planets we would see were what we called hot Jupiters. These are Jupiter-sized planets that orbit really close to their stars, close enough that they can orbit the whole star in like 10 days or less. Really close.
That's a lot of birthdays.
Yeah, those planets are super old. But just like in terms of their years.
Yeah.
Like their personal years. And people were confused. They were like, Jupiters should only form far away from the star because that's where you get the gases and the ices that will combine to form this type of planet. Why are we seeing so many of them close to the star? And so there was this big debate that's still kind of going on over whether these planets formed in situ. So like, did they form in that location, or did they form somewhere else and then migrate? So a lot of people are studying the migration patterns of planets so that we can learn more about hot Jupiters.
Whoa. I can't
Yeah.
believe I had no idea that they would switch. But again, space is so much bigger than I think. Like I really think of the solar system in a very 2D model because that's like how it was originally presented to me. So I have to imagine this like 3D thing where they like it's not like checkers where they're like hopping over each other. Like there is literal space to move around.
I would love that though.
Yeah.
If it was just them leapfrogging one over the other.
It was just strategic, and that's why they did it.
No, they move by each other usually when they're nowhere near each other because space is really big. Those are the two things that I think people don't know about space, or at least they don't understand the full magnitude of how big space is and how dynamic space is. A lot of people think of space as something that's static, that's not changing. It changes all the time.
Yeah. I get that. I think it is scary to think of it as changing. It makes it feel like the deep depths of the ocean or of like this mystery and like who knows what's there. And like that is all true, but I mean, that's why this podcast is here, so that it doesn't feel horrifying.
Right. I mean, I actually am very comforted by the dynamic nature of space because it has always been dynamic. To me, the really scary change would be if space stopped changing.
This is the movie The Core again. You gotta see it. It's one of the worst movies you can imagine.
We gotta do an episode reviewing The Core.
A Patreon episode doing The Core, maybe. Yeah, the core stops turning and he has to go in.
Yeah, when you have this system, like the universe, that is constantly in flux and then it stops, that to me is the true scary thing.
I did just get a chill.
So I like that the universe is constantly moving and changing, including on scales small as our solar system.
Hey, it's Corinne, here to give a shout out to our amazing patrons who are supporting this podcast. Thank you, as always, to our Sun Like Stars, Sharn Llewellyn, Finn, and Ian Williams. And of course, thank you to our latest pre-moon sequence stars, Becca Tizard, Charles Hunt, and Ash Meyer. You too can support us, hear your name on the podcast, make it to our patron star chart, all by supporting us on Patreon. Find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to patreon.com/palebluepod.
Hello, friends of mine and friends of the universe. I have a podcast recommendation for you. It's Star Tripper with 2 exclamation points. It's a travelogue podcast of former file clerk Festin Pixis as he searches for the zowiest experiences the galaxy has to offer. And I know the galaxy quite well. There are a lot of zowie experiences out there, so go follow Festin Pixis on his adventures. In the tradition of classic sci-fi, anime, and Saturday morning cartoons, you can dive into the action and explore the thriving cosmos with Festin and his crew as they zoom through an intergalactic death race, battle a mega beetle live on a popular cooking show, navigate their way back from the eerie dunes of the package dimension, and chase a local interdimensional cryptid. No big deal. There's so much more in these adventures of Festin Pixis. And also, the show has fully immersive sound design, killer music. The sound design is by the same person who does the sound design on Pale Blue Pod, so how could it not be awesome? Plus, there's an unquenchable can-do spirit that makes this show an instant mood lifter. Popular Science called Star Tripper pure joy in a zippy little sci-fi package, and Polygon put them first on their list of podcasts that are unabashedly positive. Don't we love positivity here? There are 2 complete seasons and 2 space holiday specials for Arbor Day and Pervoween. You'll know what that is if you listen to the show. They are available now, and you can listen to them on your pod bank of choice or go to the website startripperhq.com. startripperhq.com. And you will not regret it.
Join the Party is an actual play podcast with tangible worlds, genre-pushing storytelling, and collaborators who make each other laugh every week. DM Eric and the emphatic players, Amanda, Brandon, and Julia, welcome everyone to the table. From longtime RPG players to folks who've never touched a role-playing game before, you are all welcome here. And if you're not sure where to start, hop into the campaign, the Monster of the Week story set in a weird and wild summer camp, or marathon the D&D games. Jump into campaign 2 for a modern-day comic book superpowered story, or campaign 1 for a high fantasy epic. Whatever adventure you choose, you're invited to hang out each month for their after party, a session held to discuss campaigns, joke around, and answer listener questions. So what are you waiting for? Pull up a chair and join the party. Search for Join the Party in your podcast app or go to jointhepartypod.com.
So that is the Earth's revolution around the sun. Now we can talk about the sun's motion around the entire galaxy, which I think we've talked about a little bit before. But I can give you numbers now. So I'm not going to use miles because miles here would be so useless. Like I would have to tell you truly huge numbers. So I'll give you the speed in miles per hour, but the distances now are in light years.
Okay.
The sun is 25,000 light years from the center of the Milky Way galaxy, about. The whole diameter of the Milky Way galaxy is about 100,000 light years.
Okay.
So we are like halfway between the center and the edge of the Milky Way's disk. And I would really love to paint you a little word picture here so that everyone is imagining the galaxy in the same way that I do. Because when I close my eyes, I have this like gorgeous, vivid map of the Milky Way. So Corinne, if you'd indulge me for a second and close your eyes.
Let's do it.
And let's imagine the galaxy. So there's this inky black void around it, and you're zooming in on the Milky Way galaxy. In the center, you see this chaotic bulge. It's a spherical region where there are a lot of stars packed tightly together, and they're moving on weird orbits like figure eights and X's, and they're passing by each other, and that's a chaotic time. But outside of the bulge, you have the disk, the beautiful swirling disk of the Milky Way with its spiral arms, and they're all spinning in one direction. And then around that disk, you have the dark matter halo that you can't see because it's transparent, but imagine feeling the weight of all of this invisible matter around you.
Whoa.
That's the Milky Way floating through space.
She's beautiful.
She is beautiful. And our sun is in that gorgeous, circularly moving disk of stars where the spiral arms are. Most of the stars in the disk move on orbits that can basically be called circular. So we know that we are 25,000 light years from the center. It takes us about 230 million years to orbit. So we can do that equation again to figure out our velocity around the center of the galaxy. And it is roughly 500,000 miles per hour.
Ooh, boy, okay. That Dramamine is... I can't do anything in the face of this.
No, we're just moving real fast around the center of the galaxy, but it still takes us more than 200 million years to make it all the way around. The sun is like 4.5 billion years, which means it's done about 18 orbits around the center of the galaxy. The sun's an adult.
Finally. Still a little teenage. Thinks it's all grown up.
Right, but back when the dinosaurs were around, the sun was still a minor.
Yeah.
So now we have to deal with the adult sun.
Yeah.
And I think I would rather deal with a child sun.
I love kids, so I would love a child star.
Therein lies the difference between you and me, Corinne.
Well, we balance each other out perfectly.
Yeah. So that is the sun's motion around the galaxy, and it is very similar to a planet's motion around a star. Anytime you have this big, massive object in the center, and then there's stuff orbiting around it in a disk, that can be described as Keplerian motion. So Kepler's laws can be applied to that type of motion, but it only works under those conditions, where there's a massive thing in the center and then other stuff orbiting around it. By the time you get out to galaxy clusters, they aren't organized in the same way. There isn't like a single identifiable central mass, and there isn't a simple disk that things are orbiting in. So this is the last stage where Keplerian motion is going to be important for the velocities. But as we've talked about in the episode about Dr. Vera Rubin, we know that the rotation curves of galaxies aren't as simple as just like straightforward Keplerian motion. Because with Keplerian motion, the further you are away from the central massive object, the slower you move. So we talked about rotation curves of galaxies in that Vera Rubin episode. We expect that the velocity of stars should decrease as you get out to the edge of the galaxy, but instead it kind of flattened out, and that was an indication that there was some massive object out there keeping the speed of the stars faster than it should be. Ooh, spooky. So the sun is at a point in the galaxy where we are still experiencing pretty Keplerian motion. We're not too affected by the dark matter halo or the massive stars outside of our orbit. But it does affect us a little bit, because instead of moving on a perfectly circular orbit around the center of the galaxy, the sun and other stars in the disk move with what we call epicyclic motion. Have you heard this word, epicycle?
I have. I couldn't tell you where or what it means, but I feel like I've heard it. Maybe it sounds like a medication to me, so maybe I'm thinking of something completely unrelated.
It does kind of sound like a medication. You may have heard it when you were doing space camp stuff and talking about the slow march towards heliocentrism, because back when people thought the Earth was the center of the universe, they would have to explain things like retrograde motion and seeing planets move in a way that didn't make it seem like those planets were moving around us. So they explained it using epicycles. They said that those planets were moving on their own little circles as they were also circling around us.
I Google image it, as I often do, and I see these like shapes around the little loops, which look a lot like what I would like doodle in a notebook or something. Yeah. So the sun moves on one of these epicyclic orbits. It's kind of like take a giant slinky and stretch it around so that it makes a circle, so that it connects with itself. And that's what the sun is doing. It's like spiraling as it's revolving around the center of the galaxy. And it gets that spiral motion because of gravitational influence from other stars around it, like pulling it up, pulling it down, pulling it out a little bit, and just deviating it ever so slightly from its circular orbit. Whoa, that's a lot of movement.
Things are moving. That's what this whole episode is about. Things really are moving. They're booking it out there.
Oh, I found a GIF that kind of was the first time when I realized, oh, we're moving around the sun and we're moving forward in a way, or wherever. And I'll share that on the Instagram, everyone.
Please do. I know which GIF you're talking about. That's one of my faves. It's a good one. So that's the motion of the sun around the galaxy at about 500,000 miles per hour. You can add that to our rotation speed and our revolution speed around the sun, and you're getting like 560-something thousand miles per hour as a total velocity. But now we have to talk about the motion of entire galaxies as a whole. So we are moving within the galaxy, but the galaxy itself is also moving. We are now outside the realm of Keplerian motion. So the Milky Way is moving mostly because of gravitational attraction to another galaxy in our little cluster called Andromeda. You've heard of Andromeda?
I have.
I love the Andromeda galaxy.
I love that name.
Andromeda is from... A lot of our space names are from Greek mythology. Andromeda is a princess in Greek mythology, although she's said to be Ethiopian, but also historically the definition of what Ethiopia is and who gets called Ethiopian it's complicated. But I think the name means like man-eater.
And there she goes. Is she gonna munch up the Milky Way next? Is that what's coming?
That is what's coming. I just want to check that it does mean that. Oh.
Not at all. That's just what we want her to be.
It means leader of humankind. Where did I get this man-eater thing from? Oh, well. But Andromeda, the galaxy, is named after the constellation Andromeda because that's what the galaxy appears to be in. Like, that's its position on the sky. That constellation is named after the princess. It's a whole thing. But I do love the Andromeda galaxy, and so does the Milky Way. They aren't really moving on a straight line towards each other, although it kind of seems like it. Technically, they are both orbiting the center of mass of their system, but they're just like moving towards each other. If we know, and we do kind of, know the mass of both objects, we can calculate the force of attraction between them. And one of the most useful equations in physics is F equals ma. Force equals mass times acceleration. With their mass, we can calculate the force, and we know their mass, so that means we can solve for their acceleration towards each other. So we know their velocity and an estimate of when they should collide. And we've done this calculation so many times. It's actually a pretty common calculation for early career astronomers, like people who are still in training to be astronomers. But we know that Andromeda is about 2.5 million light years away, and that the two galaxies will really collide in about 4 or 5 billion years, although their extended halos are already touching. Like, this collision is already starting, and it will last billions of years, which is really cool. And they are moving towards each other with a velocity of about 250,000 miles per hour. Which I think is interesting. The sun is actually moving around the galaxy faster than the galaxy itself is moving towards Andromeda.
Oh, yeah.
Mm-hmm.
I mean, I'm so used to these numbers being something I can't fathom or like big and huge, and of course, but that feels like, obviously I could not survive that speed, but like it feels like a speed that's manageable. Like, I was watching the new Avatar, and there's a scene, I don't think this is a spoiler. There's a scene where they like have this special like liquid, and he's like, this can stop human aging. This is going to go for $80 million. And I'm like, only $80 million? You're not getting your money's worth, dude.
That's fair. For something that stops human aging, it should be more valuable.
It should be like
there are billionaires.
I don't even know.
No one should be able to afford that.
Yeah, right? I'm like, 80 million? To do 80 million? I cannot do 80 million. But it feels like a number, maybe.
Right. So the point here is that these numbers feel kind of familiar to you.
Yeah, they do.
Yeah. And to your point, Corinne, about you not being able to survive these speeds, you already are. We're already moving at these speeds.
I know, and here I am on the ride.
So yeah, in about 5 billion years, the Milky Way and Andromeda galaxies will collide. And I would love to just spend a little time here talking and thinking about galactic collisions, if that's okay with you, Corinne.
Yeah, what is on the other side of this?
Yeah, so I will sometimes talk about the eventual collision between Andromeda and the Milky Way. When they collide, astronomers have given them a couple name. They'll be called Milkomeda, which is, it's fine. It's
like
fine.
Like the Benefer, yeah.
Yeah, it's the Benefer of galaxies. So this will happen in about 5 billion years. But in general, galaxy collisions are quite common. Right now, like as we speak, astronomers estimate that anywhere between 5 and 25% of galaxies that we can observe are actively involved in a merger or a collision right now. Mergers were much more common in the early universe, and that is indeed how a lot of bigger galaxies got to their size. They are the outcome of many smaller galaxies colliding with each other.
Oh, okay.
Mm-hmm. And anytime you see a really big elliptical galaxy, remember back to our episode on galaxy shapes, those big elliptical galaxies are likely the outcome of mergers between smaller spiral galaxies. So galaxy mergers happen all the time. There are, broadly speaking, 2 types of mergers. Minor mergers happen between galaxies of unequal size. So if the Milky Way galaxy were to collide with a dwarf galaxy like the Small Magellanic Cloud, that would be considered a minor merger. And it all has to do with like the ratio of their masses. These mergers are actually pretty common now. They're the most common. And the Milky Way does this all the time. Like just a billion years ago, it had a pretty consequential minor merger with a galaxy called Gaia Enceladus. Right now, there's this stream, this thing called the Sagittarius stream that astronomers are actively studying right now, and that is left over from the Milky Way absorbing or having a minor merger with the Sagittarius dwarf galaxy. So this is still happening, and astronomers are having a grand old time trying to figure out which parts of the Milky Way came from other galaxies.
That's gotta be fun. That sounds fun.
Yeah, and you can do it in a few different ways. You can study the chemical. Usually these leftovers will be clusters of stars that we call globular clusters. And we can study the chemical composition of those globular clusters to see if it matches the rest of the Milky Way. If it doesn't, we assume that it comes from another galaxy. We can also study the motion of these globular clusters or the streams, right? Like the Sagittarius stream is this stream of stars left over, and we can study their motion and their shape to figure out if they came from another galaxy. Like essentially, if they're moving too fast, then that's an indication that they are from a galaxy that had some energy, it had some momentum when it hit the Milky Way.
Oh, wow.
So those are minor mergers. There are also major mergers that happen between galaxies of more equal size. So the merger between Andromeda and the Milky Way will be a major merger because their masses are pretty similar. When these mergers happen, I'll focus on major mergers here. When a major merger happens, the galaxies don't just like come together and hit and then stick. It's kind of like a dance. They are moving on orbits, even though they appear to just be moving in a straight line. So they'll pass by each other a few times, exchanging material each time, until eventually they have like absorbed each other's energy and they do stick together, and then they'll have a whole new shape. So if you have two spiral galaxies coming together, they'll dance, they'll pass by each other, and what's left after that is most likely not going to be a spiral galaxy. But when that happens, when they are doing that dance, a lot of people get worried that the stars will actually collide. That's not going to happen because the space between stars, the distance between stars is so much bigger than the size of the star itself. I saw this one comparison that I loved. It was if the sun is the size of a grapefruit, and that sun is here in New York, the nearest star, the nearest grapefruit is all the way over in San Francisco.
Oh, wow. Okay, yeah, that makes sense because like I said earlier, it's feels so 2D when you like think of it, because that's kind of how we are taught on paper. But again, it's not checkers. There's all this space.
There is a lot of space. So yeah, the stars will just pass right through each other, but the gas will collide. And when the gas collides, it will hit each other, it will condense, and it will set off this cascade of forming new stars, which is very exciting. But yeah, that's galaxy mergers. They happen all the time. I highly recommend you look up galaxy mergers, especially Stephen's quintet is one of my favorites to look at. It is 4 galaxies actively merging. And then in the image we see, there's this 5th galaxy that is technically much closer to us, but it does look like it's in the quintet. So I like to say that those galaxies those 4 galaxies are colliding, and the 5th galaxy is just, like watching.
It's just here to watch.
It's just here to watch. There are exhibitionist galaxies, there are voyeur galaxies, and Stephen's quintet perfectly
These are cool.
That.
I am looking at a picture. We'll put that on the Instagram too.
So in my book, The Milky Way, an autobiography of our galaxy, I wrote about galaxy collisions as romance, but also as cannibalism, because galaxies eat each other. So I was like, yeah, all of these minor mergers, that's cannibalism. That's galaxies eating each other so they can survive. But major mergers are romantic flings. And some romantic flings are very emotional. There are a lot of feelings involved, and the 2 galaxies will make a life together, like a marriage. And that's what the Milky Way and Andromeda are going to do. They're going to come together, they'll combine their lives, and what's left will be something that is unlike whatever the 2 galaxies had before. But there are also some galaxy mergers that are more fleeting than that. Like there are flings, there are hookups in these galaxy mergers where sometimes the galaxies have a flyby, but they don't really merge that well, or
they'll leave a shirt at the other one's house, and
exactly. Some galaxies are polyamorous, like in Stephen's quintet, where they want multiple partners merging at the same time. So yeah, in the book, I wrote about galaxy mergers as one of the main ways that galaxies interact, and I had to anthropomorphize it, and I had a lot of fun thinking about how queer and kinky these galaxies are.
There is a theme in today's episode of all the kinks.
Oops. Yeah. Okay. So that's galaxy mergers. So again, we're coming back to the velocities where if we add it all up between the Earth's rotation and revolution, the sun's revolution around the galaxy, and the galaxy's motion towards Andromeda, we are now at like 750 miles per hour.
Okay.
Mm-hmm. And that is if it all happens to line up like in the same direction, which is very unlikely.
Mm-hmm.
But now we get to the motion of galaxy clusters as a whole. The Milky Way and Andromeda both belong to a little galaxy cluster with about 50 or so galaxies in it. We call it the local group. But there are also other clusters of galaxies nearby, and clusters of galaxies can come together to form super clusters of galaxies. Fantastic. All of these clusters can move together en masse, and we know that we are. Back in the 1970s, when astronomers were trying to better understand the cosmic microwave background, they were pointing their telescopes all around the sky. And they noticed that we are moving very fast in a direction that lines up roughly with the center of the galaxy, which we used to call the zone of avoidance because there was so much dust and gas and like black hole stuff and stars in the way that we couldn't actually see anything on the other side of our galaxy if we looked towards the center. So we noticed that we were moving towards this big thing, but we couldn't see it to figure out what it was until our ultraviolet, like our UV and our X-ray and our infrared telescopes got better.
Yeah.
So then we were finally able to look into this zone of avoidance, and we were able to see what was attracting us.
A huge eyeball that's staring back at us.
Just a big eye. Can you fucking imagine? That'd be so scary.
That would be the scariest thing I've ever heard. I'm sorry to scare anyone who's
just
already
a big
afraid.
Sauron eye out in space.
Yes, exactly.
Looking at us from the other side of the galaxy. No, thank you. No, luckily space isn't that scary. They were calling this thing that we're moving towards the Great Attractor for a long time, from the 1970s, and it's only recently that we figured out what it was. So it seems that it's the central focus point of a giant supercluster of galaxies that we call the Laniakea supercluster. So when we finally were able to see into the zone of avoidance, we started seeing more galaxy clusters with thousands of galaxies in them. One of them was the Norma cluster that had 1,000 galaxies in it and was like 1 billion times the mass of the sun. Then we saw something called the Shapley cluster. This has more than 8,000 galaxies in it, and it's 10 quadrillion times the mass of the sun. That's 10 followed by 16 zeros.
Oh my gosh.
And the Great Attractor itself is like the central point in all of these galaxy clusters. We're moving at it. We're zipping through space towards this Great Attractor at a speed of 1.3 million miles an hour.
Oh my gosh, that's really fast.
Oh, your gosh is right, Corinne. We're moving so fast. So that brings our total velocity, our maximum total velocity through space to 1,000 plus 67,000 plus 500,000 plus 250,000 plus 1.3 million, which is basically just 1.3 million.
Whoa. Yeah.
So I guess if you zoom out far enough, our motion is dominated by this gravitational attraction we feel to the Great Attractor. But yeah, we're moving through space very, very quickly.
That is really fast. And to think that I can walk around as if nothing's happening.
I know. To think that there are people, like, you have to learn that we are moving.
Yeah.
Even though we are zipping through the universe at 1.3 million miles an hour.
That's really crazy. I did look up what the fastest, like how fast a person has ever been. And of course there's like, if we put these people in a rocket and they went this fast or whatever, but I meant just like a regular human on their own. And maybe you know the name Usain Bolt, but he set the record for the 100-meter dash in 2009. And there's a New York Times article that kind of tracks his speed during that dash. He did it in 9.58 seconds, which
Ridiculous.
Is crazy. And he peaked just after the midpoint of this record at 27.5 miles an hour, which feels crazy just to do on your own. But I did try to find what we can do, and it seems like we can briefly hit 27.5 miles an hour if you're the fastest man on the planet.
Got it. Well, it's good to know what our bounds are as a species. Interesting. Yeah, so if you are listening to this episode in a car or on a plane, you can add your personal velocity to this equation, but know that with that 1.3 million mile an hour factor at the end, it's not going to make much of a difference, unfortunately. But yeah, that is how fast we are moving. So if anyone ever tries to tell you that you're like, I don't know, breaking a speed limit or something, tell them, well, officer, I'm already moving. We're all already moving at 1.3 million miles an hour. Hey, Corinne, you know what time it is?
Is it time for our riding lesson?
It is. Our appointment's coming up, and I see them saddling the elephants, so let's go.
I can't wait.
And wherever you are, however fast you're moving, listeners, please remember that you are space.
Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.